Okay, so this video is going to be about the tubular functions of the kidney, mainly dealing with reabsorption and excretion. But first, I just want to go over some basics here and just talk about the main functions of the kidney, which include maintenance of body composition, uh, excretion of metabolic end products, foreign substances, and also remember the kidney does some secretion of enzymes and hormones. But we're not going to discuss that as much today. Okay, so the main function I want you to keep in mind today is this maintenance of body composition. And to help understand that, I do want to talk about the balance concept, which is really important to understanding renal physiology. So remember, the body likes to keep certain things within certain parameters, like pH, extracellular fluid volume, and the concentrations of different ions. So in order to maintain homeostasis of these different parameters, basically the amount that goes into the system has to equal the amount that comes out of the system in order to keep this value stable. Disease occurs when this is imbalanced a certain way. So a lot of organic compounds, usually they're produced through metabolism and then they're consumed or excreted in some way. That's how balance is maintained. But for things like electrolytes and water, which um, are ingested, basically to maintain balance, it has to be excreted via the urine. And everything we're going to go over today is really going to show you how the kidney maintains balance in electrolytes and water. So since the kidney's job is to maintain the composition of all the body fluids, it's important for you to know what is in each uh, body fluid. So here we have a cell, and here's the intracellular fluid, and here's plasma, and these are the concentrations of the ions in each type of fluid. And so the kidney works hard to maintain these concentrations within their uh, uh, fixed ranges in each type of fluid. The main things worth noting are the differences between these two. So look at potassium. So most of potassium is intracellular. And look at that. Sodium, the concentrations outside the cell are high, but it's quite low inside the cell. Likewise, calcium is very low inside the cell. Magnesium is mostly intracellular. Extracellular fluid contains a lot of chloride and a lot of bicarbonate, okay, compared to intracellular fluid. Look, things like phosphate and organic ions tend to be concentrated in intracellular fluid. So keep these in mind as we move through the next couple of videos. Okay, so you may remember that the normal GFR is 125 milliliters per minute, or that's 0.125 liters per minute. So if you calculate this out for 24 hours, that comes out to be 180 liters per day. So that's a lot of fluid, right? So I've drawn it out here. Like this is 180 liters of plasma, and that's how much fluid your kidneys filter in a given day. Okay. However, look over here. This is a little jar containing about 1.5 liters of urine. So I hope you're wondering, well, how do you get from this to this? Because what goes into the tubules after it's filtered from the glomerulus is this. But then what comes out in the urine is this. So certainly something must occur. And if you're thinking about reabsorption, you're right, that's what occurs. The kidney reabsorbs most of what is filtered. So now I put a list of things that the kidney absorbs and the things that the kidney primarily excretes. So things that we want to hold on to, even though they get filtered, include water, sodium, chloride, and bicarbonate. And the kidney is going to reabsorb about 99% of these things because these are good things that we want to hold on to. If we need to get rid of them, then the kidney wanted to do that. The kidney also absorbs about 50% of the filtered urea. But in addition to holding on to the good stuff, remember the kidney wants to get rid of the bad stuff. And so it's going to excrete metabolic end products and toxins. For instance, creatinine is excreted, uric acid gets excreted, the other 50% of the urea gets excreted. a little bit of phosphate and a little bit of potassium gets excreted, but also the toxins, so uremic toxins, and also drugs as they're metabolized. All this stuff is what is preferentially excreted in this 1.5 liters of urine right here. So what we're going to go over today in the next couple of videos is how the kidney preferentially reabsorbs what it wants to, but also how it excretes what it doesn't want to reabsorb. Okay, so this is a simple schematic that shows how reabsorption rather, and secretion occur. So here's the afferent arteriole, here's the glomerulus, there's the efferent arteriole leading away from the glomerulus. And what's important to note is that right after the efferent arteriole, the blood vessel becomes the peritubular capillary, and it hugs the tubule from then on, allowing close contact between the two and transfer of solutes. So I put some terms over here. So the filter load would be, here I'll put an F just for space. So this represents the filter load. The fluid that comes right out of the glomerulus right here represents the filter load of some solute. And you could calculate that by measuring the concentration of that solute in the plasma and just multiply it by the GFR, okay? Whatever ends up in the urine, here we'll put it here, is the excretion. And so a substance is excreted at a certain rate. You can measure that by simply taking the concentration of that substance in the urine, right? And just multiply that times the urine volume, and you'd get some sort of amount of substance that was excreted. Now, it's tough to measure reabsorption and rates of secretion directly, but we can measure it indirectly, simply by finding the difference between these two. So if something gets reabsorbed, so here let's draw something reabsorbed. So let's pretend like a solute got filtered, and then there, it's getting reabsorbed. So I'll put an R for reabsorption. You can measure that by calculating the filtered load, so how much came out of the glomerulus, and then subtracting the excretion, how much actually came out in the urine, and that would give you a measurement of the reabsorption. What about a measurement for secretion? That's moving in this direction. So if something secreted, it, whatever it was, it did not get filtered very much, and it would move from the peritubular capillary into the tube. I'll put an S for secretion here, just to save space. So to measure the rate of secretion, all you do is measure what was excreted and subtract the amount that was filtered, okay? Okay, so now we basically just zoomed in into a cartoon showing tubular cells, and this is the different ways that solutes are transported across tubular cells. So just to orient you, this is the tubular lumen on this side, and on the other side is where the blood is. Tubular cells have polarity, which really means that the two sides are different. They're not the same. The side facing the tubular lumen is called the apical side, and the side facing the blood or the interstitium is called the basolateral side. So if you notice that we have a few ways of transporting solutes across membranes, we have transcellular movement of electrolytes. You're probably familiar with active transport, which is accomplished here by the sodium-potassium ATPase. It pulls sodium out of the cell in exchange for moving potassium in. This is probably the most important form of transport because it drives the movement of solutes in other ways. For instance, like secondary active transport. Notice this is a carrier that, in addition to bringing sodium in, or brings some other solute. I just put X, but it could be anything else. For instance, like glucose, which acts in this manner. Basically, because the sodium-potassium ATPase is keeping sodium concentrations very low inside the cell. So I'll put down arrows. So remember, if it's doing its job correctly, sodium will be very, very, very low. Now there's a favorable diffusion gradient for sodium to move from outside the cell into the cell, and that will drive the movement of this other thing, okay? And so this other thing, I'll just say X, as it accumulates inside the cell, now there'll be a concentration gradient for it to leave the cell, and it can leave through this carrier protein, which is called facilitated diffusion. It's moving based on a concentration gradient, but the carrier protein is helping it move transcellularly. Glucose is reabsorbed in this fashion. There's also paracellular diffusion, which is not across the cell, but it's in between the cells. So right next to the tubular cells, right here, we have these tight junctions, and these proteins are a class of proteins called claudins, Claudins. And so different solutes can move in between these if the tight junctions are leaky. And so in certain parts of the kidney, on the tubule, the junctions are leaky and solutes can leak around the cells and be absorbed that way. Now let's talk about secretion real quick. So secretion would be the movement of solute from the basolateral side to the apical side. There usually are transporters that can bring in certain solutes, and there's usually a transporter on the apical membrane that will actively secrete something into the lumen. And this is how we can selectively get rid of certain toxins, certain drugs. If we have a buildup of potassium, potassium can leave the cell to get rid of hydrogen ions can leave the cell. So this is secretion.